So let me first consider a finite system of subwavelength resonators. So I take n of these resonators. These are the speeds of the wave inside these resonators. These V, I'm assuming that they are comparable and they are of order 1. Then in each resonator, I have a high contrast, delta 1 up to delta n, and I'm assuming that these guys here are small. Okay. So what can be proved? We can prove that this finite system of subwavelength resonators has n subwavelength resonators. There exists n resonant frequencies here to the equations where D is this union of n disjoint resonators. So this can be proved. Now, in order to compute these resonant frequencies, we can discretize a boundary integral formulation, some boundary integral formulation like this, and then we can use Miller's method in order to compute the characteristic value of this boundary integral formulation. For given delta, we compute the omega from omega 1 to omega n, the resonant frequencies here, as characteristic value of this boundary integral operator. This is fine. But what I'm going to show you is a discrete approximation of our PDE model in order to obtain accurate numerical approximation of these subwavelength resonance frequencies with significant reduction in computational power. So either we consider the PDE model and we can formulate this some integral equation, and then we can solve or find these resonance frequencies as characteristic values of such an operator, or we can form a matrix, n by n matrix, compute its eigenvalues, and the eigenvalues and the eigenvectors can be used in order to approximate the resonant frequency of the systems and the resonant modes. The resonant modes are the solution to these equation with u incident is equal to 0 and corresponding to one of these resonant frequencies. Good. So let me show you the numerics first. Okay. So let's take n spherical resonators. Delta is set to be equal to 1 over 5,000, and then we compute by discretizing our boundary integral formulation. We can discretize and make use of this multiple expansion method, our favorite method, in order to get the resonant frequencies here. There will be 10 resonant frequencies for the system of subwavelength resonators. If we compare this with respect to our discrete approximation, then we get accurate results and we reduce significantly the computational power, as you can see here from these numbers. So our discrete approximation is based on this capacitance matrix formalism or concept. So let me introduce you to this. So let's denote C, this generalized capacitance matrix with entries given by this. So Cij here are obtained by inverting the single layer potential, which is this convolution operator with the fundamental solution of the Laplacian. This is the characteristic function of the boundary of one of the resonators, and we integrate them, we get entries of this capacitance matrix. Then we weight this capacitance matrix by multiplying it by these coefficients. This is in terms of the volume and the material parameters. We get this matrix here. We compute the eigenvalues of that matrix. We take their square roots, and these square roots of the eigenvalues of that matrix are approximately the resonant frequency we are trying to find up to leading order. Okay. So if the material parameters are all real, so I call this the Hermitian case, then the C would be symmetric matrix, and it has n eigenvalue here. And as you can see here, the resonant frequencies have to be complex because of this radiation effect, okay? Because of the Sommerfeld radiation condition, if you like. Nevertheless, their real part is of order square root of delta, while their imaginary part is at most of order delta. Okay. So we approximated the resonant frequencies using the eigenvalues of this capacitance matrix, which is discrete approximation of our PDE problem. And we can do the same for the eigenmodes. The eigenmodes, the resonant modes, can be approximated in terms of the eigenvectors of our capacitance matrix by multiplying these eigenvectors with the single layer potential of these densities here. The single layer potential corresponds to convolution with the outgoing fundamental solution of the Helmholtz operator. Good. Now, how about when we eliminate our system of resonators? How about the scattered wave? So if we eliminate our system of resonators with a frequency which is of order square root of delta, this would be a real frequency, because this is a physical problem. Then the solution can be decomposed in this form here. So look at the sum. It can be decomposed over the resonant modes, where the coefficients here can be obtained by inverting this linear system here. So you neglect this reminder, you invert, you get the coefficients here, and as you can see, these coefficients blows up when the frequency omega of the incident wave is very close to one of the resonant frequencies. Cannot hit one of them because all of these guys are complex, but they are complex with a small imaginary part. So there is strong enhancement of the scattering. Very good. Now, how about n equal to 1? If I have only one resonator, then this eigenvalue of the matrix, that would be 1 by 1 matrix, and the eigenvalue would be this one here, square root of delta. This is the real part, delta the imaginary part, and now the capacity of this single resonator enters into play. So the real part is approximated by this, the imaginary part is approximated by this, and the scattered field is of monopolar type, because the scattered field is proportional to the Green function. This is the fundamental solution of the Helmholtz equation at the location. So far away, we see that, or we can approximate our resonator as a point source with scattering coefficient given by this. And if you see, if you take omega close to the real part of the sky, which is omega m, then there is a strong enhancement near this monopolar resonant frequency. So I'm calling this monopolar because the far field approximation is of monopolar type. It behaves like a point at the location of the resonators times that's of course the incident wave at the location times the scattering coefficient, which blows up. Okay. Now, how about considering a dilute system of subwavelength resonators? Because as I said, metamaterials are composites. They are made out of this out of this resonator. So let's consider this dilute system of subwavelength resonators. What we can prove, and this is what we did with Haisen a couple of years ago. What we can prove that this system, you can describe it by an effective operator. If you are looking at the far field, at the scattered field from an incident plane wave. So there is an incident plane wave hitting your resonators, then you look at the scattered field, and the scattered field, you can compute it out of this effective operator, where V now, this effective potential, has this form here. The coefficient here depends only on the size and number of subwavelength resonators. V tilde depends only on the distribution of the centers of these subwavelength resonators. And when omega is slightly below this omega m is the resonant frequency of one resonator, because my system is dilute. So basically, there is a weak interaction between all of these resonators. The resonant frequency of the whole is approximated the resonant frequency of one resonator. Slightly below, there is the medium is behaving with high contrast effective couple. And then, this is what we did in a series of papers with high. Then we can prove that we can achieve super resolution imaging or super focusing by considering this imaginary part of the Green function of the effective operator and proving that it has sharper peak than the free space one. When omega is slightly above omega m, the medium now is with negative effective couple. Of course, the effective medium theory does not hold when omega is exactly equal to omega m, because adding or removal of one resonator from the system affects the whole field, the total field, by magnitude of order one. Okay, so there is no limit when the number of resonators is going to infinity. Okay, having negative effective kappa is is nice, but the challenge is to have double negative effective material properties with negative kappa and negative effective negative rho. This can be done using dimers instead of distributing single subwavelength resonators. We can distribute inside the domain omega dimers. So these dimers are consisting of two identical resonators. We can prove that a resonator dimer can be approximated by not only point scatter, like a single resonator, but with point scatter with resonant monopole mode and the resonant dipole mode at two different frequencies. But these frequencies are close to omega m, and these frequencies we call them the hybridized resonant frequencies of the dimer. And what we can show, we can obtain negative effective kappa and rho for some frequencies near these hybridized resonant frequencies of a single dimer. Very good. Now let's keep thinking about this dimer. So I take D1 and D2 under this symmetry assumption and this time symmetry assumption. Now I'm considering material parameters with complex coefficients, and I'm assuming that the material parameters here are complex conjugate of the ones. Okay. So let's call this V1 square delta. V is the speed of the wave, and delta is this contrast between the densities, between the rho inside and outside the resonator. So let's write them like A plus IB. B is the magnitude of the gain and the loss. And what we can prove that this system of parity time symmetric system of subwavelength resonators has asymptotic exceptional points. So the statement is there is a magnitude of B, there is a magnitude of gain and loss, such that the resonant frequencies and the corresponding eigenmodes coincide at leading order in delta. Okay, so this is due to this PT symmetry assumption. So this parity times symmetry assumption, which forces the spectrum of the capacitance matrix to be conjugate symmetric. If you look at the PDE model, it's not PT symmetric. And this is due to the radiation condition. If you complex conjugate your Sommerfeld radiation condition, you get, instead of outgoing waves, you get incoming waves. Nevertheless, because our capacitance matrix is an approximation to leading order of what's going on for the PDE model, our exceptional points for the capacitance matrix are somehow asymptotically true for the PDE model in terms of this small parameter delta. Okay. Now, okay, how you can see this? It's very simple. Just we know that the resonant frequencies are complex square roots of this eigenvalues of the capacitance matrix. There is explicit formula for this, and you can see that the eigenvalues coincide if B is chosen such that this guy is equal to 0. If B has this value, this corresponds to a point where the capacitance matrix has a double eigenvalue, and we can check that the corresponding eigenspace is of dimension 1. Okay, so this is what I said about the complex conjugate nature of the spectrum of the capacitance matrix. B0 is here. For B larger than B0, the spectrum is complex conjugate, and for B smaller than B0, the spectrum is real. So we call this value B0, the value which corresponds to this exceptional point. Okay, now that exceptional point we have made here two eigenvalues coinciding and the corresponding eigenvectors coinciding. We can make it at higher order, we can make it the nth order exceptional point. So these are eigenvalues of algebraic multiplicity equal to n with corresponding eigenspace of dimension 1, as you can see here. What's the significance, or what's the application of this? What is the motivation for us to think about this nth order exceptional points? The motivation is enhanced sensing. So assume that you have a system with such a singularity, such a degeneracy, like if a small particle is introduced into such a system, then we can prove that there is a splitting in one of the resonant frequencies of the system, and that the splitting is of order the nth root of the particle volume. So this makes your system extremely sensitive to extremely small particles. Here I'm showing you examples of this PT symmetric systems with third order exceptional point. This is the choice of, so you take 3 resonators and you take this B is equal to some value here and minus B here, and you can prove that such system admits a third order exceptional point. And this is the one with fourth order exceptional point. This is the distribution of this material parameters V squared times that. Good. Okay, so up to now, our resonators were unmodulated. Okay, so let's start to modulate the resonator and see what's going on. So we'll get a kind of a very interesting new physics and new phenomena, and I hope we'll get you excited about this. Okay. So instead of considering this Helmholtz equation, this is static regime, we consider the wave equation. Why? Because now our material parameters are depending not only on x, so they take 2 values, one inside the resonator, one outside, but also they are depending on time. And these dependence on time is periodic with some period capital T. So they are slowly depending on time. And what we want to characterize the quasi-frequencies of such system. How to do it? Which are in the subwavelength regime. So taking the Fluke transform in T, we end up with this same equation. And now we have this quasi-frequencies. So what we want to find omega such that there exists a solution to the wave equation, which is non-trivial, and which is when you multiply it by this exponential minus I omega t, it's T periodic in T. Okay. So let me call omega is 2 pi over the T. This is the frequency of modulation. And the interesting physical regime is to take omega as square root of delta. You remember when we considered unmodulated case, the resonant frequencies, the subwavelength resonant frequencies, as I said, were of order square root of delta. So let's take the modulation in time also of order square root of delta. Okay. So I'm calling y star t is the time brilliant zone. And if you think about it a little bit, there is kind of ambiguity. Why? Because if you add to omega any multiple of this guy, if there is a non-trivial solution to this equation with omega, this would be a non-trivial solution with omega plus n omega. So there is kind of folding. Okay, so it does not somehow make any sense to look at subwavelength quasi-frequencies in this brilliant zone, because you can get any quasi-frequencies into the subwavelength regime. Nevertheless, we need to add a new condition, and this is for the time-dependent case, which is the following. We call quasi-frequencies, so omega such that there exists a non-trivial solution to this equation, a subwavelength quasi-frequency if the corresponding solution or the corresponding mode, if you like, is essentially supported in the subwavelength frequency regime. Means you expand U like this. This is Vn of x, and most of the energy is in the leading order terms, in the m first terms. And we need to assume that m times the square root of delta is going to 0 as delta is equal to 0. So it's a small. So you can go high, but not as of order 1 over square root of delta. Okay. So here, with this definition, I think this is the right definition of what is subwavelength quasi-frequencies. We can prove that they are n subwavelength quasi-frequencies if D is this union of disjoint n subwavelength resonators, and we can compute them exactly as in the unmodulated case using our capacitance matrix formulation. So how it works? What we can prove that when delta is small, the quasi-frequencies to leading order are given by the quasi-frequencies of the system of Hill equations. So you can see here that we have our our capacitance matrix, which was of use with key use, if you like, in the unmodulated case. So we have system of n equations, ODEs. We solve these systems, and for each solution, we compute its Fouquet exponent. Okay, so computing the Fouquet exponents of the solutions of this Hill system of equation gives us these quasi-frequencies, this subwavelength quasi-frequency. Now, if you assume that all the kappa are not modulated, there is no modulation in the kappa parameter, and all the rho are modulated in the same way, you can reduce this Hill, the system of Hill equation to this system here, where now you have the capacitance matrix. But this is exactly the static case, because the quasi-frequencies will be approximated by the square root of this capacitance matrix. And this is exactly what I showed you at the beginning. So we recover the unmodulated case by just making all the modulation in kappa equal to 1 and all the modulation in rho the same. Okay. Now let me move to periodic systems, because interesting physics is there. So let's consider n resonators repeated periodically. This could be repeated periodically in 1 dimension, 2 dimension. We get screens. 1 dimension we get chains, and in 3 dimension we get full crystal. Okay? I'm using standard notations for the periodic lattice, the fundamental domain, dual lattice, and the Brillouin zone. Okay, so what we want to compute the subwavelength spectrum of our original problem. So we have this Helmholtz operator, and we want to compute the subwavelength spectrum of the original operator. So this is standard. We can show that the subwavelength spectrum, the spectrum is the union of the spectra of the quasi-periodic problems, and the subwavelength 1 is the union of the subwavelength spectrum of the quasi-periodic problems. For each of these quasi-periodic problems, since we have n resonator repeated periodically, we have n discrete value of omega, of resonance frequency. We have n resonance frequencies, and then we consider these eigenfrequencies as function of the quasi-periodicity, and we obtain the band function. So let me show you how to approximate these resonance frequencies here for the quasi-periodic problem. We do exactly the same. We can approximate them as the square root of the eigenvalues of not the generalized capacitance matrix, but the generalized quasi-periodic capacitance matrix. Okay, so I will define this generalized capacitance matrix. The same for the resonant modes. Okay, we take the eigenvectors of this generalized quasi-periodic capacitance matrix. We'll multiply them now by these quasi-periodic single layer potentials of some densities here defined as usual, and then we get our resonance modes. This result here, this approximation holds only when alpha is away, when the quasi-periodicity is away, far away from 0. It's not uniform in this Brillouin zone. I will be back to this. Okay, so what's this capacitance matrix? So the capacitance matrix, in order to introduce it, we need the single layer potential associated with the quasi-periodic green functions. It has this form here, and we know that for alpha non-zero, away from 0, the single layer potential has this expansion. Okay, as the frequency or the wave number, if you like, goes to 0, it has this expansion. This expansion does hold only away from 0. Okay, because of this assumption, expansion, our capacitance matrix makes sense only away from 0, because this guy here is not invertible when alpha is equal to 0, when we are considering the periodic case. Okay, so let's introduce this capacitance matrix away from 0. Compute its multiply it as usual by this material parameters and divided by the volume. And as I said, if you compute the eigenvalues of this guy, taking the square root, you will get approximately this band function as a function of alpha away from 0. Fine. Now, what's going on near 0? How we can approximate? So what we want to approximate this band functions using discrete approximation of our system. So if we are away from the periodic case, from the gamma point in this Brillouin zone, this can be done as I showed you. Okay, because this capacitance matrix is exactly this quasi-periodic one is exactly the matrix or the discrete approximation we want. Near 0, we should take the limit not when alpha goes to 0, but when omega, we fix alpha 0 and take the limit when omega goes to 0 of the single layer potential of omega alpha 0 omega. This, it turns out, the inverse of this guy is holomorphic. It has this expansion here. So we can introduce this in very analogous way, this periodic capacitance matrix. It's here. And what is remarkable is that this definition is independent of alpha 0. So we have, even for this first radiation continuum near 0, for this quasi-periodicity near 0, we have the right concept of generalized periodic capacitance matrix, and it's given by this one. Now, what you do, if you want to look at what's going on or study what is going on in this first radiation continuum, near alpha is equal to 0, you compute the eigenvalues of this guy, you take the square root, and this is approximation of the resonant frequencies near this first radiation continuum. Okay. Very good. So these are simulations. So this is square crystal. When you have a crystal, one resonator repeated periodically to make a crystal. This is 2D case. And since there is one resonator, there is only one subwavelength band function. Okay, this is the one here. And as you can see, there is a band gap. This is well separated from the second band structure, which is not band function, which is not in the subwavelength region. So any frequency here cannot propagate into the crystal, and the frequencies here, because this is band gap, subwavelength band gap. Any frequencies here is with wavelength which is much larger than the unit cell of the crystal. Okay. So as I said, this capacitance matrix here in the periodic case is used to understand what's going on here near this point gamma in the Brillouin zone. This corresponds to the periodic case. Okay. This curve here attains its maximum at this point in this corner of the Brillouin zone, and what we can prove, this is because of symmetry. What we can prove, and this is what we did with Hayes and Hyundai Lee 3 years ago. We can prove that the eigenmode, this block eigenmode, has two-scale behavior. Okay, for frequencies or quasi-periodicity which are close to this M point here, to pi. Okay, we can prove that it's a rapidly oscillating function on this at the small scale, as you can see here, and there is a large scale envelope which satisfies a homogeneous equation. I will show you this later. Okay, sounds good. So this is the envelope, and this is a high frequency oscillation. So there is the solution. The eigenmode is the product of some envelope with a highly oscillating function. Okay. Now, as I said, we want to trap or guide waves at subwavelength scales. How do we do this? Because we have this band gap. What we can do, we can create defects inside this band gap by just detuning resonators with an upward shifted resonance frequency inside the band gap. If we can do it, then this would be defect mode. Okay, so waves here in the detuned resonator would be trapped at exactly this frequency here, and we can achieve subwavelength trapping of waves. Okay. The wave here would have a wavelength much larger than the size of the resonators. Nevertheless, it stays inside this resonator. So how we do this? There are two regimes, either the weak interaction regime or strong interaction regime. This depends on this distance between the resonators compared to their size. In the weak interaction regime, we decrease the radius of one resonator, and in the strong interaction regime, we increase the radius of one resonator. And the shift between these two regimes is at this condition here, when the resonator's radius would be equal to the resonator separation. I will show. I will be back to this when we consider the topological properties of materials. Okay, so we can prove that there is a defect mode. So mode, flat curve here inside the band gap, well separated, not well separated, but still it's away from this continuum spectrum. This is the numerics. As you can see, it's well trapped. This defect mode is well localized. We can do the same for guided waves. We can make a line defect, but now the perturbation has to be large. Otherwise, we cannot get this eigen modes, this band here away from the continuum spectrum. So the perturbation has to be large. Then the analysis is kind of tough, and that's what Sun-Yun Liu and Eric Hiltunen did. Okay, so we make the perturbation large, and we can prove that they are defect modes. In order to prove this, they are modes which are localized to and guided along the line defect, and we have to prove that there is no bound modes. This curve here cannot be flat. Which is a kind of a technical thing to prove, but we managed to do it. Okay, this is waves guided into this line defect. Okay, and as you can see, they are exponentially decaying in these directions here. Now let's move to and play with some geometry. Okay, let's consider this honeycomb lattice. So honeycomb lattice, you can make it out of dimer. And as I said, for dimer, there are two band functions, because there are two resonators. There will be two band functions in the subwavelength regime. And it turns out, because of the symmetry, these two band functions, they cross each other at some symmetry point, which is this K point. Okay, so at this K point, there is a Dirac point, and near that point, the band, the first band and the second band, they behave like this, and because of this behavior here, there is a conical behavior of these bands. At that K point, the first eigenfunction, the first eigenfrequency is of multiplicity 2. And at that point, there is what we call Dirac point. Okay. Now, what's the behavior of the eigenmode here? Okay, the block eigenmode for alpha close to this alpha star corresponding to this K symmetry point. For alpha close to alpha star, the mode can be decomposed like this. Okay, up to some reminder. S is the size of the crystal, and delta is our small parameter, this contrast parameter. It's the sum of these two. Each of them is some envelope satisfying an effective equation, a homogenized equation like this, times something which is oscillating. So in the case of a crystal with a square crystal with one resonator, we get only one of these two, right? When we have a dimer in this honeycomb structure, we have some of these two, and each of them is satisfying this effective equation. If you consider this vector u1 tilde and u2 tilde, the envelopes, they satisfy the Dirac equation. Okay. So look at this effective equation. The frequency here is near zero, means that there is almost zero phase shift propagation if you send a wave inside this crystal, this honeycomb lattice of subwavelength resonators. So which is great. Means that we can achieve kind of propagation of waves over long distance with almost zero phase shift. Nevertheless, because we are at this K symmetry point, there is low transmission, so we cannot couple the incident wave with the structure, and I will try to show you why. intuition of why this is the case. If we want to have high transmission, then we need to move this Dirac singularity to this point here, to the gamma point, to the periodic, to move it to, if you like, this is what I call the first radiation continuum. Okay? And then the coupling will be high enough, and then we will get this zero phase shift. So without modulating the resonators, there is no way to do this. So here are just some numerics you can on the oscillation of the eigenmodes. As I said, there is a sum of two envelopes multiplied by highly oscillating function, as you can see, and this is contrasted with the square lattice. And as you can see, the period here is much larger than the period here. Means that this guy here for the honeycomb structure is much closer to zero than for the square lattice. So what we want now, we want to move this Dirac singularity to the origin. So let's consider modulated resonators. And so modulated resonators, as I said, wave equation with time-dependent material parameters, which are periodic with respect to time, with some period t of and further 1 over square root of delta. Okay. So taking both in t and x, taking this Fluke transform in t and x, the problem is the following: we fix alpha, we want to find omega, such that there exists non-trivial solution to this equation here. Great. So how to approximate those quasi-frequencies, those subwavelength quasi-frequencies? We solve a system of Hill equation now with this quasi-periodic capacitance matrix, right? So just we add alpha in our old formulation. We compute the Fluke coefficient of each solution, and there will be n number of resonators, which is repeated periodically, and we get all of these band functions. Okay, so let's consider this two trimers and make a honeycomb structure out of this. So these two trims are kind of special. Why? Because there is one is kind of we make a shift in the modulation. So it's modulated like this. And here with a phase equal to 0, 2 pi over 3, 4 pi over 3. So we have kind of a pseudo spin effect. Okay? And the other one, we make it in the other direction. So we have one turning in some have some orientation, and the other one have opposite orientation. And we make a honeycomb structure out of this. And what we can prove that for the M modulated without no modulation, the Dirac singularity is here at K point. And when we start to modulate, we can make the Dirac singularity at gamma point, which is great. This is Dirac singularity for our honeycomb structure. So here we can achieve a high transmission, couple incident wave with this modulated structure, and have no phase shift over long distance long distance in those materials. Very good. Something which is recent. This is with Eric Hiltunen and my new outstanding PhD student Jinhao Kao. We consider exactly the same. Okay, so exactly the same structure, and we can prove that we can find omega, the modulation, this frequency modulation frequency, and epsilon, which is the amplitude of the modulation. This is the modulation frequency. This is the amplitude for exactly the same structure with this pseudo spin nature, such that the propagation is non-reciprocal. Means what? Means that this band function are not anymore symmetric with respect to the origin, with respect to alpha is equal to 0. Moreover, there is band gaps, which is not symmetrical. Look at the second one here. If you take this is band gap only for alpha negative, and the other one is disjoint from the first one, and it's only for alpha positive. So if you take a wave here with a frequency inside this band gap, it will not propagate from the, let's say, from the left to the right. Okay, It propagates only from the right to the left and not from the left to the right. So we achieve this non-reciprocal wave propagation by using this kind of well-designed time modulated system. Okay, we can have also exceptional point degeneracy in such time modulated things. And this is what Tia Kosh, she got a complete theory of this. Okay, playing with the modulation and with the modulation. So we can show that we can find modulation frequency such that at that modulation frequency there is exceptional points in the time domain. There exists alpha 0, such that below that guy the spectrum is real, and above that guy the spectrum is complex conjugate. Very good. So why we are looking at those degeneracies? The main reason is looking at those degeneracies is interesting physics is when we have systems either with this direct degeneracy or exceptional point degeneracy, and we open those degeneracies into band gaps. Those band gaps, as I will show you, will have non-trivial nature, and then we can make all of these properties of guiding or localizing more robust to changes or to impurities or defects in the system. Sounds good? Okay, so briefly, since I showed you this non-reciprocal wave propagation with time modulated things, we can have the same, but we can have unidirectional transmissions in screens like this with complex material parameters under this PT time symmetry. And the reason is okay. The reason is we can get, as I said, unidirectional transmission, and the reason is the existence of exceptional point degeneracy in such systems. Okay, without this degeneracy, there is no hope to do something which is which is classical, if you like. Okay. Okay, so let's consider these guys here. We can compute the eigenvalues, and as you can say, we can make them equal coincide. We can make these eigenfrequencies coinciding and the corresponding eigenmodes coinciding to leading order in delta by taking B equal to making this guy is equal to 0. So B is given by this formula. And as you can see, the exceptional points depend both on the geometry and the quasi-periodicity alpha. It gets complicated. So close to this first radiation continuum, close to this gamma point, the system is always below the exceptional point. The exceptional point is here. For larger alpha and for large enough B, there exists a quasi-frequency, a quasi-periodicity alpha 0, as you can see it here, such that there exists an exceptional point. Okay, of course, above this. Above this alpha 0 here, the alpha 0 is here. The band structure consists of two bands which are complex conjugate to each other, as you can see here. Okay. Now, in such systems of screens, we can achieve unidirectional transmission. We can prove that there exists frequency such that the screen's reflection coefficient is asymptotically close to 0 when the incident wave is from one side, and non-zero when the incident wave is from the other side of the screen. And this frequency here is inside, remarkably, it's inside this first radiation continuum. It's close to the part where alpha is 0. Okay. We can also so this is the unidirectional transmission. So there is transmission only from one side. And we can make extraordinarily high transmission by tuning this parameter B. So we can prove that there is critical B. It's here, the critical gain to loss parameter B, such that there is a huge peak in the transmission of such a PT symmetric screen. Okay. Okay, here everything is complex. So gain and loss allows the scattering matrix to be non-unitary, and the reflectance and the transmission to, of course, exceed 1. There is no conservation of energy. It's like the time modulated case. We have to put energy into the system. So there is no conservation because we are putting energy into this. Okay. So these results are based on this computation, which are explicit of the subwavelength structure of the subwavelength band structure close to the origin in this, as I said, first radiation continuum. So there is a lot of interesting physics. Okay, so maybe I can skip this, but just if we look at this band structure close to the origin, there are a lot of other interesting physics. So this is what we did for the phenotype transmission anomaly. Somehow this Heizeng and Johnson Lin did great work for other periodic structure, and we did it here for subwavelength resonators. So you take a screen of dimers repeated periodically, then you can prove in the periodic case that it exists frequency which is embedded within the continuous radiation spectrum, which is the spectrum of waves. I have been talking about this for forever now. The spectrum of waves that can propagate into the far field, but remarkably, the eigenmode associated to this omega-2 cannot be coupled to the far field, cannot interact with incoming waves. And then the idea is that to have the symmetry of this screen broken slightly. So then the real frequency omega will be shifted into the complex plane, and the corresponding mode will be coupled to the far field. And now you have to design the system in such a way you have a huge interference between your omega-1 and omega-2. This is a dimer. There are two frequencies. You need to make omega-1 with large imaginary parts. You need to shift this omega-2 into the complex plane, and you need to make them highly interacting. And then doing this, you can show the existence of asymmetric peaks, which are known as phenotype transmission peaks. This is the guys. Okay, sounds good. So the symmetry is broken slightly, and you have from one side is the transmission behavior is not the same as from the other side. So, this is the phenotype. Very good. Okay, I promised you to discuss this robustness. So let's do it. Robustness of this guiding at subwavelength scales. So let's do it in a few minutes briefly. So I show you the idea, and then I will conclude. Okay, so as you can see, general principle for trapping and guiding waves at subwavelength scales is to introduce a defect into this periodic arrangement of subwavelength resonators. Okay, but this is sensitive to imperfection. Why? Because these curves here are very close to the continuum spectrum. So the goal is to design subwavelength wave guides whose properties are robust with respect to imperfection. And then the idea is kind of to do the same as in condensed matter theory, introducing this topologically invariant, which will capture this crystal wave propagation properties, and then prove that there are topologically protected edge modes, something which is localized but not sensitive to imperfection as the guides. Okay. So the idea is simple, but then you have to put it into work. And this is we are lucky because we can do it through our discrete approximation of this PDE model. Okay. So we take two crystals with topologically different wave propagation properties, means different values of the topologically invariant. Join half of the first crystal, I call it A, second crystal B, and at the interface, there is a chance to have a topologically protected edge mode, and this is known as the bulk boundary correspondence principle. So for our business, let's take this chain of dimers. We know that the dimer has two bands, and these bands can cross each other at the Dirac singularity. And let's try to open that Dirac singularity or degeneracy into a non-trivial band gap. This is what we are going to do. So with dimer under some symmetry assumptions, this is distance d, this is distance d prime. D prime is the period minus d. And then what we can prove? We can prove that, okay, so let me introduce this that face. You take it from this SSH business in topological insulator theory. It's you compute first the Berry-Simon connection, which is there are two modes, right? Each mode has its resonance frequency has a mode. So you compute this guy here for n equal to 1 and 2 for the two modes. So you integrate over the resonator. This D is the union of D1 and D2. Then you integrate this Berry-Simon connection over the whole Brillouin zone, and you get a phase. So it's called the Z phase, which corresponds to the parallel transport around this the whole of the Brillouin zone. And it turns out for us that the Z phase is exactly the change in the argument of one of the enters of our quasi-periodic capacitance matrix. Great. We can compute, at least in the dilute regime, and we can show that it takes value pi if D is larger than D prime. It takes value 0 if D is smaller than D prime. And if D is equal to D prime, we have a Dirac cone. So basically, we are opening this Dirac cone into non-trivial band gap. Okay? And you can interpret this in terms of band inversion between the cases D is smaller than D prime and D is larger than D prime. So when D is smaller than D prime, as I said, is the period minus the distance separating the two resonators. You get monopole, then a dipole. And when D is larger than D prime, you get a dipole. This would be the lowest curve, and then the monopole. Okay? And D equal to D prime, you have this Dirac legionnaire. Very good. So now you take, as I said, half of this structure with Z phase equal to pi, 1 equal to 0, and you can prove that there exists a protected edge mode, which is, of course, robust to imperfections. Here there are simulations. This is the topological protected edge mode, and as you can see, it's robust to errors in the resonator positions. While if you take a chain of resonators and you change one of the resonators size, you will get a defect mode. But that defect mode its stability is really poor. It can be easily lost among the other eigenvalues. So these computations are done for finite chain. Right, very good. If you are familiar with quantum mechanics, this idea of discrete approximation is very similar to tight bending approximation. Now we clarified the link between the two. And let me mention that significant difference between these two is that for classical waves, we cannot approximate our capacitance matrix with a three-diagonal matrix, while in quantum mechanics, the very popular approximation is to use on the top of the tight bending approximation the nearest neighborhood approximation. So tight bending approximation is basically dilute approximation, while our capacitance matrix, it takes into account strong interaction between the resonators. If you have a set of n resonators, our capacitance matrix is taking care of this interaction between the resonators. Okay, so you can do the same for non-Hermitian things. Now you take dimer with two different material parameters, and you repeat it periodically, and this would be half of your structure. The other one, you swap the material parameters, so you don't change the distance, you keep the distance the same. And what we can prove that, as you know, in this non-Hermitian system, they are exceptional degeneracies. And what we can prove that we can open this exceptional degeneracy by swapping kappa 1 and kappa 2. Okay, so this is the analog of this non-Hermitian Z phase. Now you have because the problem is non-Hermitian, you have a right eigenmode, left eigenmode. You compute the Z phase like this. You need to take care of the right and left eigenmodes. and you can prove that it's not quantized. Nevertheless, it can be used. It can be used to predict topologically protected edge modes. So by this, let me conclude my talk. So I think the basic idea is on all of this system, you have to create degeneracies and try to open these degeneracies into non-trivial band gaps. If you can do it, then you have robust, you make all of this extraordinary properties of guiding, manipulating, or controlling waves. There is a chance to make them robust with respect to imperfections. We got very much excited about this time-modulated things, and I think that there is an avenue for understanding many of these extraordinary physical properties and such systems. And this brings us to kind of comparison between the classical world and the quantum world. And I'm kind of confident that in the classical world we can reproduce many of this quantum mechanics phenomena by modulating the system, in nice way. Thank you so much. I hope you enjoyed.
So thank Professor AMMARI for this very interesting talk. And if you have any questions, you can ask either in the chat box, and it would be better that you can unmute yourself and ask to Professor AMMARI directly.
Okay, can I ask a question?
Yes, please.
Okay.
How are you?
Thank you, Habib. Thank you for a nice talk, and you give us a lot of information. So I will ask start from the bottom, the latest one, the last few slides about the topological edge state. I mean, you know, there is a paper by Weinstein and Pfefferman in Princeton National Academy of Sciences. They talked about topological project edge state in the model of a one-dimensional shielding equation, right?
Yeah, this is here. Yan, this is exactly.
Oh yeah. That's right. But of course, in a lot of discrete models, that's much easier that you can show the existence of topological edge state. SSH models and so on, a lot of discrete models. But their paper is a one-dimensional shielding equation model. Okay, asymptotically periodic in two different directions. Yeah. So I was a little confused about exactly what model you are doing. I mean, you seem to have a SSH kind of lattice, and for the high index contrast particles and so on. And then you also talk about capacitance matrix and so on. So what I'm saying is mathematically exactly what are the underlying equation? Is it a Helmholtz equation? Is it a 2D Helmholtz equation? It is supposed to be 2D Helmholtz equation.
Yeah, it's a 2D Helmholtz equation.
Yeah, like the pictures that you showed, one of these pictures. So it's really for the 2D Helmholtz equation.
Yeah, it's 2D Helmholtz equation. Yeah.
Okay, so then you make the left and right sort of different with the periodicity, and then you argue the existence of the local edge mode, right? That's what you did.
Exactly.
Yeah. Okay, and so then but then is this a rigorous mathematical proof for the general Helmholtz equation, or it's asymptotically? Is the result only valid in the asymptotic limit of this high contrast?
Yeah, it's valid only in the asymptotic limit of the high contrast.
Okay.
So the reason is the following. So the PDE model is too complicated. Then you approximate it by this capacitance matrix, which it does the same job as the tight bending approximation.
Yeah, but tight bending is very, very simple. The tri-diagonal matrix is a lot easier. Yeah.
Now, okay. Now, all the physics is there. So this Zach phase is exactly this Zach phase is exactly the change in the argument of this guy here.
Yeah.
Okay. And now you compute the change of the argument in this guy here, right? Yeah. What we can do, we can do it only in the dilute region.
Okay.
We think that this is true in the general regime, but we can do it only in the dilute regime.
Okay.
In the dilute regime, this is discrete. It takes 0 and pi.
Okay.
And we have this Dirac cone, degeneracy, and so on and so on. Right.
Okay. Okay, that's good.
And for the non-Hermitian case, so this is kind of improvement because over this, so you don't change the geometry.
Yeah.
You swap the material parameters.
Yeah. Yeah.
So these are complex, but you can take them complex conjugate to each other, and then you swap them, and then what you can prove, you can introduce the Zach phase here.
Okay.
Similar. And based again on this discrete approximation, you can prove that even though that's not quantized, but the structure can support localized eigenmodes. Yeah. Under these assumptions, you need this imaginary part to be larger than the real part over something. So you are in this broken PT symmetry case.
Yeah.
If this is the case, then the structure supports localized modes. Or if kappa 1 is not equal to complex conjugate of kappa 2, then if there is no PT symmetry, we can prove that there is localized modes without having the Zach phase, the corresponding phase, Zach phase in the non-Hermitian case, without having it quantized. It can be done. Right?
Okay, thank you.
And the phenomena here is completely different because we open the degeneracy of the exceptional points, not the direct points. There is no direct points.
Okay.
For the time modulated things, I tried to show that they possess exceptional points and also direct degeneracy, and actually we can play with both.
Okay.
In the time domain.
Okay. Just maybe I guess I'll ask one more separate question, and I mean it's a relatively basic question. So, namely, you consider two topics. One is the time modulated periodic lattice and of this kind of high index object, nanoparticles, small particles, subwavelength particle. The other one is you consider pairs, consider PT symmetric. So you put the gain or loss into the particles, and so then they both exhibit some kind of some kind of asymmetry for one side to propagate this side, and for PT symmetric case, you have zero refraction in one direction, then then the refraction is non-zero on the other side. And then for time modulated, you also have non-reciprocity. So I guess my question is, what is the motivation of doing time? What is the significant advantage of doing this time modulated system?
So compared to this PT symmetric business?
Yeah, PT symmetric, you already have some nice things about the one direction is quite different from the other direction.
Yeah, I would say, okay, okay. So we don't know how to make Dirac singular degeneracies inside this PT symmetric stuffs. It doesn't make sense to me, right? So, while for time modulated, you have both. You have exceptional point degeneracy. So non-Hermitian case, to me, it's exceptional point degeneracy. Yeah. Hermitian case is this Dirac degeneracy. The time modulated, you have both.
I see. Okay, so that's one mathematically part of the this difference.
Yeah.
Okay.
So this time modulated and non-Hermitian, of course, you need to put energy into the system, but it looks like the time modulated looks like a more exciting because you have all kinds of degeneration.
Yeah, I know. I mean, time modulated things. A lot of people are now studying this. Yeah. PT symmetry is more or less for a while. It has been there for a while, so it's not generally that much excited.
Yeah, because there are very few results on general non-Hermitian systems, right? And the only one we can analyze is this non-Hermitian system under this parity time symmetry.
Okay, thank you.
Very small subclass of problems, right? So while in the time domain, it's fun.
Yeah. Okay. Thank you.
Thank you very much. Thank you.
Thank you.
Okay, so yes, any other questions from the audience?
Oh, okay. I got a very small question, maybe. Habib, thank you so much for this such an exciting talk with so many wonderful results.
Thank you.
So I got a question about this your screen structure. So for that part, I think there's a screen got 3 dimensions. So all those 3 dimensions are within this subwavelength regime, or there is 1 dimension is beyond the subwavelength regime.
So the structure we are considering, this one is the screen. So it's a 2D periodic structure in 3D.
Okay. Oh.
So basically, I'm sorry, so somehow there is no difference. So how I classify it here. So you take d dimension of periodicity, d dimension of the ambient space, and you get these cases here. So whether the difference is 0 or 1 or 2, and then the analysis is basically the same.
Oh, okay.
So here you need 3, 1. So it's a chain of resonators. There's a 3-dimensional spherical resonators, if you like, in 3D, and you make them periodic in 1 direction. But this one you take it 2, 1 or 3, 2. That's fine. This is screen, and this one you have to make it to 2, 2 or 3, 3 to have it crystal. And the analysis is in each case is the same. Of course, there is a difference between these 3 cases, but in each class it's
okay. Thank you. It's very interesting, I think. Okay, so that's all my question.
Okay, so any other questions from the audience? Okay, so if no, then if there's no more questions, then let us thank Professor AMMARI again for this very interesting talk. Okay.
Thank you very much. It was my great pleasure to give this talk and to see many of you. Take care. Thank you so much.
Thank you very much.
Thank you.
Thanks.
Okay, Habib, you take care. We'll see you.
Yeah, take care.
Okay.
Thank you so much.
Okay.
Okay, bye-bye.
Okay, bye-bye.
Bye.
Bye.
Bye-bye.
Bye. Thank you.
Thank you.
Thank you.
Thank you.
Thank you, Hong. Take care.
Thank you, Habib. Take care. You take care. Bye-bye. Bye-bye. Take care.